Hello, and welcome to a conversation on friction and normal forces. To start with, we're going to talk about normal forces. It's come up in a couple of conversations previously that normal forces are forces that stop solid objects from penetrating each other. We can think about this in a variety of situations. We can think about it as if you get a hand on a friend's chest and you push your hand not penetrating the chest is what causes that person to move. You can also feel that chest pushing back on your hand. You can think about it as the force due to gravity is pushing you down through the ground, and the normal force from the ground is stopping you from going through it. You could think about it as if you're running as fast as you can and run into a brick wall. The pain you feel is actually the normal force from the wall that's applying a force to your face or chest or whatever thing that actually hit it. The main rule for normal forces is they always are perpendicular to the surface. Perpendicular to the surface. So in our gravity example, where you've got a floor or a chair or a table and something's sitting on it, the normal force would always be acting up on that object. If you're on a ramp or a slope, it would be acting perpendicular to the surface, so it would be acting at an angle. And if there was, say, you were pushing something against a wall, like you could hold a book against a wall, or if you ran into that brick wall, the normal force would be acting perpendicular to those. We've been talking about a lot of forces, so it's probably relevant to add that for a normal force, it's usually an F with a little subscript capital N, and that's pretty universally recognized as the symbol for normal force. If we look at our simplest example for now, and we're going to stick to example 1 for this chapter, but for examples 2 and 3, we're definitely going to look at next chapter for sure. So don't memorize this, just use it as a bit of an algorithm for critical thought. Do not memorize any of the forces stuff. Really, there's a ton of variation that we can add to them. So if we look at example number 1, the normal force, if you imagine, say, somebody standing on the ground. As we talked about, there is a force due to gravity acting down on them, and there is a normal force acting up on them. We can see that if this person is just standing there, they're not going anywhere, then the force due to gravity in this particular scenario must be equal to the normal force. So if an object is not moving on a horizontal surface, then and only then Fn will be equal to Fg. So our normal force will be equal to the force due to gravity. And we talked about in the previous lecture that Fg is frequently equal to, if we're talking about the surface of the planet where we know what little g is, we could calculate that using mg. If we don't know what little g is, then we're stuck using Newton's universal gravitational law, which is not too much more complicated to use, but definitely involves some bigger numbers. gm1, m2 over r squared. And that's what a normal force is. We could look at an example if we want. Let's call it example 1. Let's say a 50 kilogram book rests on the table. What is the normal force acting on the book? acting on the book. I always, whenever we're talking about forces, like to draw a little picture. There's our surface, there is our book. I know that acting down on it, there's going to be a force due to gravity, and the reason it's not going down is because there's a normal force. Therefore, the normal force is going to be equal to the force due to gravity. Since it hasn't said otherwise, I'm going to assume that this is on Earth, which is a good thing to do all the time, unless it says like space or planet X or planet Y or spaceship in orbit. If it doesn't say anything spacey, it's on Earth. So my normal force is going to be equal to mg. So my normal force is equal to 50 times 9.8. So my normal force is equal to, I think that's a 49, actually, sorry, 490 newtons. And so that's kind of how normal forces work. I'm just going to change this so it's full page. So what we want to talk about next is friction. So friction is a resistive force. That acts to stop things moving. And there are three kinds. Kind number one is static. So this is something like there's a great big huge boulder sitting on the ground and you push on it and it doesn't move. So object is not moving. On a smaller scale, you can imagine a book on a table and you try and push it very lightly with one finger. You're applying a force, you can feel the force on your finger, you know that force is being applied to the book, but the book still doesn't move until you push hard enough and then it starts to move. Before it starts moving while you're applying that force, this is a static friction. Number two is sliding friction. So any object that is sliding, there is some sliding friction. So if you slide, you're pushing on that book and you poke it with your finger and it starts to slide, there's sliding friction between the book and the table. So an object is sliding. The third type is rolling friction. So if you imagine a ball rolling down a ramp or along a floor, it's neither static nor sliding, and so we have what's called rolling friction. We're not going to talk about rolling friction much more in this course. It's a little bit more complicated than both static and sliding friction. But it's just worth bringing up that it's a thing and that it exists and that it's important in day-to-day life too. For static and sliding friction, the force of friction, it's equal to mu F N. So FF is our force of friction. Just like every other force, it's measured in newtons. And Fn we just talked about, it's our normal force. But mu we haven't talked about yet. And mu is how sticky or grippy those two surfaces are, and it's called our coefficient of friction. It is different for a bunch of different surfaces, and you can look it up online. You can look up coefficient of friction tables, which I've started doing already. And what looks like a good one? This looks like a pretty good one. Notice how there's two columns on this coefficient of friction table. There is a static friction, which is the first column, and a kinetic friction, which is the second one. So kinetic is the same as sliding, and static is that first one. And notice how static for all of them is a little bit higher than the kinetic friction, that sliding friction. So what that means is you push on something, push on something, push on something, and then eventually it sort of gives. And most people have felt this. I think it's really good on ice. If you're pushing a goalie net on a hockey game, you can like give it a push, and then once it starts moving, it's easier to keep moving, and that's a very real thing. That is experimentally determined, and everybody experiences that. So these kinetic coefficient of frictions, the static coefficient of frictions, you wouldn't have to know. You definitely don't have to memorize them. They would either be given to you on a worksheet or a test, or it would ask you to calculate it. So that's our kinetic coefficient of frictions. To find them in reality, we just there's a couple of different experiments that they do. There's no real mathematical way to determine them. It's interesting to note there's a couple of industries that are super interested in developing materials that either have a super high coefficient of friction or a super low coefficient of friction. Super high coefficients of friction, Stellies is in a pretty unique place because we could talk about climbing shoes. Obviously, more expensive rubber is stickier rubber, and there's a whole industry out there trying to develop really expensive, really sticky rubber for climbing shoes. A more universal application of high coefficient of friction rubber is car tires. So if you have car tires that can have a super high coefficient of friction, it means that when you go to stop, you can stop much faster. Super low coefficients of friction would be any industry that's working in automotives. So any car, any train, anything, especially for rolling friction, you want that coefficient of friction to be as small as you can so that you can burn less gas as you go and just keep it going. You don't have to overcome that force of friction. Coefficients of friction. So coefficients of friction depend on the two surfaces that are rubbing together. And then other than that, it really only depends on the normal force. So normal force and coefficient of friction are the only two things that a force of friction relies on. Coefficient of friction in reality is subject to temperature as well. So different substances change depending on whether you heat them or cool them, but it's not universal, and we don't typically talk about it. So at any given temperature, you've got a coefficient of friction that's pretty consistent. So if we look at an example, I think we're on example 2. If we think of I don't know, I'm bored and say a book again, but let's do a book again. A book, and let's say it's a 40-kilogram book, so it's like a real big book. 40-kilogram book is sliding along a table. Along a table. And the force of friction is 40 newtons. Sorry, 20 newtons. 40 newtons is boring. What is the coefficient of friction? So we can draw our little diagram again, and we've got a book on a surface. Force of gravity would be going down on it. The normal force would be going up on it, and we'd have a force of friction slowing it down potentially, or yeah, it'd be slowing it down. So we're looking at the force of friction, and we know our force of friction is equal to mu Fn. And this is the formula that would be given to you on your formula sheet. In this particular instance, we are on a flat surface. It's not moving up or down. So Fn will be equal to Fg. We know, since we're on the surface of the planet, that we can use mg to calculate Fg. So mg, because Fg is equal to mg. And we're looking for mu. So I can divide both sides of my equation by mg. And I get mu is equal to F divided by mg. Notice how right now I have a force on the top and a force on the bottom, and it's worth pointing out that the units would cancel. So mu will always and forever be unitless. My force of friction which I just read out, is going to be a 20. My mass is 40. G is 9.8. And I get my coefficient of friction is 0.0510. And it should give you a funny feeling to write down a final answer without any units. And in this particular case, that's okay. It's probably worth pointing out that coefficients of friction are almost always, but not by rule, less than 1. So they're usually between 0 and 1. So this is a pretty normal coefficient of friction. It's actually quite low, but definitely in the realm of possibility. That is coefficients of friction, friction, and normal forces. I hope you are all having a wonderful day, and I will catch up with you guys next time.